Dive into the world of data center innovation with the iMasons podcast, discovering the people leading the industrial revolution. My name is Romain Trunchant, and today I'm joined by Duncan Ng, Vice President Solution Engineering at Vultr, a global infrastructure as a service provider delivering GPU and cloud computing while supporting complex compliance requirements. He has agreed to take us through the rise in density, why, how, when, and especially as a driver for liquid cooling requirements. Let's get right into it. Hi, Duncan. How are you today?
I'm doing great. Thanks for having me on the podcast.
It's an absolute pleasure to have you on the podcast today. Before we've got a lot to unpack actually, and such an interesting topic. A little bit further away from the pure facilities topic we've been having before, but nonetheless quite important for what's coming up in the next few years. Before we dive into this, I'd love you to give you for you to have a bit of an introduction, so that we can learn a bit more about who you are.
Yeah, absolutely. As you mentioned, I'm the Vice President of Solutions Engineering here at Vultr, and have been with the company. Very happy with what we've been able to accomplish in terms of rolling out capacities for these types of dense workloads across the planet. Prior, have experience, on the service provider side, as an engineer, as well as on the sales side as an account rep covering hyperscale companies in the infrastructure space. Had the opportunity to build a top 500 supercomputer in the past as well, so that experience is really helping out as we essentially are rolling out supercomputers in many more places than we ever expected to.
That's such a fascinating background and very much anchored in the IT side of our industry. Today, what we wanted to do is to really link together what's happening in the IT space, especially with the material that is coming in for AI workload, high compute workload, and the necessity that has been driving the liquid cooling parts. Before we go into all of this, I'd love to get your view on why is it that we see today the rise in density and such a sharp rise in density in the last few years. Can you take us through this?
Yeah, for that, I kind of, want to look at this from two different angles. That first perspective is just the amount of energy and therefore the heat that gets generated from these devices. How over the course of a relatively short 4 years, we've gone from servers that are looking at approximately, 10 kilowatts each for a cumulative 40 kilowatts in a cabinet, all the way to these advanced use cases that we're hearing about now, just hitting the floors at 135 kilowatts. So we can roll through that. And then, from another perspective, folks will oftentimes be like, okay, why don't we just spread these out further? There's some network effects that we can discuss as well that explain, why these densities are important and what they allow for these systems to do in the long run.
So can you give us a sense as to why those CPUs are getting more powerful? What is it that they do, or why are they different to what we've seen before?
Yeah, absolutely. So the reference architecture, for the air-cooled systems, at 10 kilowatts a piece, had 4 of these systems per cabinet that allowed you to be able to drive, to get to that 40 kilowatts with your top-of-rack switches. Even in the very short time frame of over 4 years, we've seen those single systems go from 10 kilowatts to 14 kilowatts. So all of a sudden, what was a standard air-cooled rack, now is kind of past that tipping point of where it's effectively air-cooled, and now pushing towards an almost 60 kilowatt per rack type design. What we're also seeing now that is really driving the liquid cooling is with these advent of 135 kilowatt type racks, where this is no longer in any way, shape, or form capable of being air-cooled, where that liquid cooling is the only option. In terms of the use cases, everyone's kind of familiar with the, chat style interfaces that have been so popular over the last couple of years. I'm lucky enough to work with some very innovative companies, getting to solve some pretty interesting problems. Everything from using models to solve, heat diffusion in semiconductor type applications, to dealing with, the most banal of enterprise use cases, having insurance companies fight for insurance reimbursements, but, a case of where they're applying LLM models to go ahead and help be able to push that forward.
Well, what's very interesting, and you mentioned that in passing earlier, is that the servers are getting a lot denser, and we've seen a shift from CPU to GPU as well, which again doesn't help in terms of reducing the amount of power consumed. What you and I have discussed in the past is that theoretically, if it was purely about compute, we should be able to distribute it across as many racks and cabinets and square meters as we would want to be able to help with that dissipation of heat. What's preventing this?
So I think kind of two different steps of drivers that we can look at. Everyone's familiar with the InfiniBand or Ethernet-based networks to tie these GPU fabrics together. So with the speed of these networks, everyone's used to the kind of 100-meter distances. That's a fairly large space, even with cable ladders and in and out of racks, a well-defined kind of radius that we've been able to work with. Moving to 400 gig connections, no longer are we working with that 100-meter distance anymore. We're now looking at a 50-meter distance. So all of a sudden, a standard design that's looking at 127 computers, tying this together in a 50-meter fiber radius is pretty tight already. Much less if you want to scale beyond approximately 1,000 cards to 2,000 or 4,000 cards. Now you have to be very careful about your cable routing to be able to handle that. So that's very much just a kind of GPU to GPU in the classic sense that everyone's familiar with. I think what really takes that next step, where we're going from that 40 kilowatt, 60 kilowatt, because we need to maintain those fiber distances with some of the advancements of server to server, with a magnitude higher speed interconnects, these have been technologies that have been promised for quite a while. But to get that magnitude increase, you also get the magnitude decrease in distance that you can cover to tie these systems together. So now you're looking at systems that need to get tied together on, low single digit meter connections, from one cabinet to the next cabinet type of scenario. So the only way to kind of effectively to do that is to drive very, very dense cabinet architectures so that you can line them up right next to each other and drive those types of densities to get you to 135 and not just one, multiple of them next to each other in that very tight physical space.
This is really not even a linear scale at that point when we're really shortening the distances, is because the opportunity to compute is really exponentially increasing from one generation to the next. I mean, even from my own background, we used to have SLI links between GPU cards, even in home computers. And I guess this is now being done at scale between all the servers. And again, to go back to the sort of use cases, whilst we're all familiar with the can you give me a picture of something quite banal and what system using for the first 15 minutes, you're really seeing those customers come up and solving problems at scale with the infrastructure that you put in place.
Yeah, absolutely. Example that I often use, especially here in the United States, one of the large banks has started advertising, it's still a chatbot, but it's no longer a case where this is something experimental. This is something that they're doing internally. They're spending marketing dollars to try to show that to demonstrate to their customers, an ease of use improvement, what for them, I'm sure is a lower cost of interaction, a lower cost of answering a question. And you start hearing, very large companies starting to roll out these generative AI use cases, there absolutely is value that's being delivered and delivered at scale. This is no longer a case of, you're trying it out, I'm trying it out. Oh, that's kind of fun. That's kind of interesting. This is where they're trying to reach their millions of users here in the US to be able to make those and drive that adoption.
I still remember starting my career what felt like an eternity ago, and we were talking about 2.3 kilowatt a rack. Yeah. And I'm not sure where we've gone wrong in between, but those numbers have vastly dwarfed. But even 10 years in, we were talking about 4 kilowatt, and that again it seemed quite a vast improvement, and never did we hear about somebody even using that power in a single rack. Yeah, where are we now? Can you retrace those last 4 years, just give it a sense of scale?
Yeah, absolutely. So, kind of to use the market leaders, products just as a way to talk about these generations. Looking at an A100 8-way system, that's what I was talking about, where we were looking at approximately a 10 kilowatt server. The reference architecture, to meet those density space requirements that we discussed from the network side, required 4 of these servers to kind of comfortably meet this physical footprint that you needed. Kind of thinking about how many air conditioning tiles you needed to be able to sufficiently cool, racks of these next to each other, sufficient space, for spine and leaf layers of the network, so all put together, wanting to put 4 of these servers into each of these cabinets to drive that 40 kilowatt. So as these servers have continued to develop, the current generation of machines on the air-cooled side are slightly more power demanding. The next generation of the air-cooled options, drive somewhere north of 14 kilowatts per cabinet. So even in the span of 4 years, all on air-cooled, no longer, if we're going to kind of take 40 kilowatts approximately as the limit of where air cooling is comfortably capable of doing, no longer am I able to do 4 per cabinet. I'm now doing 3, and I'm now really pushing the limits of what I can do on a air-cooled cabinet. Now we take the next step, to these new systems. You mentioned the SLI type of interconnects in commercial systems. That's essentially what this is. This is, data center SLI type connections at scale, an active based system to allow you to drive this. So instead of a single kind of single server domain on that very fast NVLink, NVSwitch type network, now they're trying to grow that, 9 times to be able to tie 72 of these together in a single rack, and then to be able to tie, the adjacent rack to form a cluster of 144 total compute GPUs in the same very fast, NVLink type connected system, as opposed to an InfiniBand connected system, about approximately a magnitude's difference in speed. So this is why you start to see this vast consolidation of power from a air-cooled solution that's even driving up the densities, having to get to these very dense, individual types of cabinets, right next to each other and not spread out, wide apart.
It's been such a quick and even accelerating kind of race for density. At what point do you think liquid cooling will become mandatory? And also, do you think actually operators around the world are actually ready for what's coming, or even for the workloads of today?
So definitely, if you're looking to adopt these 135 kilowatt, Grace Blackwell type infrastructure, liquid cooling is a must today. If you're not already talking to your customers who are looking to have these workloads, or if you're a data center customer looking to find space for this is a conversation that you should be engaged heavily with your team on both sides already. It's a situation where there's just no effective way to cool this, from an air-cooled solution in the types of densities that we're talking about here. So liquid cooling is essentially the only option. Lucky for us, in the case of things often come back around, many of these techniques were originally developed for mainframes. We're bringing significant portions of that type of thinking back in, but it's really a case of how do you find this capability in the existing infrastructure. And then in terms of, how much of it is available, I think for those who are not building their own infrastructure, who didn't plan for this, in advance for liquid cooling of this type of density, I would say kind of, single digit percentage wise of the existing data center space, that's, let's call it more than a year old, something that's been commissioned, something that's in operation, not something that's launching in Q1 of 2025. It's a very small percentage that can actually take these workloads at any type of significant scale.
That's that's very well put, and thanks for taking us through this. We're moving on from past to future. We know there is a lot of data centers being built across the world to actually house a number of those of the solutions. What is your view around all the people building those data centers, and what should they be looking out for if they don't want to be deprecated by the time that their data center is even built.
I think this is that classic case, in terms of the business planning, in terms of product management, understanding your customers, what pillars of kind of data center product are they looking for anymore? Are they looking for a standard 10 kilowatt cabinet? Are they looking for that kind of, as far as we can push air cooling, 40 kilowatt cabinet? And how much percentage of the, let's call it ultra dense, 135 kilowatt cabinets are you looking to bring into your mix? So often we've already heard in the last, year plus, data centers kind of very carefully modulating that mix from a capacity perspective, making sure that they fully understand what types of customers that they're bringing in, so that they're not taxing their mechanical systems in ways that are not effective.
Yeah, the mix of densities is going to become crucial, isn't it, in the very near future, and making sure that we actually have both the traditional compute staying within reach, so that we don't block all of the traditional things that people are trying to do, but also enabling all of those future technologies coming to the market and being able to house all of this. What I'd love to do is, just as a parting ways, what sort of materials did you look for? What is it that you would advise people to look into to further the knowledge into what's coming up to market?
I think some of the folks that are doing the best work are the team at the Open Compute team that are tracking the liquid cooling options that are out there. I've been asking questions in this space, pretty hard for the last 18 plus months. And it's a case where, last year or 18 months ago, there were still lots of, we have all of these different types of options, right? It was a case of, we know that this from a mechanical engineering perspective will work, it's where will the market coalesce to? And whereas, kind of at this point, there's kind of 2 or 3 different approaches that have been coalesced to that make sense, that, there's going to be commercial availability on, supply chain perspectives to rapidly grow this out will be there, as opposed to, science projects or one-off custom built type scenarios.
Fantastic. Yeah, I can recommend actually the Open Compute website. We've actually put the link on the screen. This is very interesting because we're really at the border between the facilities and the IT now. And that chasm that used to exist between the two, where none of the team wanted to talk together, is sort of being forced by hooks or by crooks to actually come together and really have to start working together. And before we part ways, so I'm going to put the Vultr website as well in view. If you want to learn more about what Vultr does for their clients, by all means, go and have a look. This is absolutely fascinating and definitely at the forefront of what's coming up. So I really appreciate, Duncan, you coming on the podcast today, taking us through what you see of the market from an IT perspective and an IT infrastructure perspective. On that note, for all of our listeners, we hope that was actually an interesting topic to discuss. If you too want to feature on the podcast or have any topics that you wish were discussed on the podcast, please let us know. You can email me at romain.truncheon@imasons.org or find me directly on the Mobilize app. Duncan, once again, thank you very much for coming on today.
Absolutely. Thanks a lot for having me. It was a pleasure sharing.
Take care.